So let's talk about radioactivity. We tend to cover this in New Zealand because of a New Zealand lad by the name of Dennis Rutherford, who actually did a lot of work into this area. And what he did, he was working over in England under J.J. Thomson, later took over the Cavendish lab from J.J. Thomson. And with the aid of people like Geiger and Marsden, they discovered that the atom is basically made up of a nucleus with all the electrons around it in a cloud. And the size of this is tiny. We're talking that the radius of the nucleus is approximately 10 to the negative 15 meters. Meanwhile, the whole atom is measured in nanometers. And what they discovered was in the center of this, there was protons and neutrons. So just about all of the mass in an atom is in these. So a proton has a positive charge, and it has a mass of 1.673 times 10 to the negative 27 kgs. And they also discovered the neutron. Well, the neutron was also discovered, and that had no charge, and that had a mass of 1.675 times 10 to the negative 27 kg. And why is there a difference between the mass of a proton and a neutron? And that's because a neutron, if you actually look at it, this is meant to be our neutron, it's actually made up of a proton and electron, which have been rammed together. And if you manage to isolate a neutron and leave it alone, after a while they will fall to pieces and you'll end up with a positive, negative charge and alternative hydrogen atom. But okay, so basically these things we're going to call nucleons because they hang out in the nucleus. Okay, so let's go for a second. What they also noticed, well, people like Becquerel and also Madame Curie, with the Curies, was, hold on, if we do this, clear. So this is going to be section, where are we up to, 10.2. If you have an atom, they were doing research with things like with uranium. They were trying to extract uranium. They also accidentally discovered radium. Well, they discovered radium. What they noticed is that atoms, radioactive atoms, will spit out 3 types of radiation. So there's alpha radiation. This is made up of a nucleus this is a helium nucleus. So what this nucleus has got 2 protons, P, and 2 neutrons. And they come out, and the very first thing these things try and do is they'll try and grab a couple of electrons from wherever they go. So yeah, they can be quite damaging if they get in the wrong place, but usually not much of a problem. They also discovered something which is called beta radiation. This is basically a high-speed electron that gets spat out of the nucleus. And we'll go into more details in these in a little later section. You also get gamma radiation, which is a high-energy photon. So this is much higher energy than light. So light, visible light's approximately, 4 electron volts. These things can be, gamma can be approximately 600 million electron volts, even more. You know, so these gamma rays can have huge amounts of energy associated on that tiny little scale. So we'll go through each of these types in the next video. But what we'd better do is, so we can talk about where these things come from and what happens when these electrons and these particles get spat outwards. We'd better develop a notation. So what we're going to do, so this is going to be section 10.3. So what we're going to do is we're going to designate a way of writing atoms. So often, if I'm writing carbon, This is your standard carbon, carbon 12. I might write number down. What I have here, the number, this is going to be, when I write this, so this is going to be the chemical symbol. And that you just pick up off the periodic table. Okay. So that's going to be, so for hydrogen it's H, for lithium it's Li, for gold it's AU. This is going to be the number of protons. Because the thing is, the number of protons determines what the element is. So if it has one proton, so I should say number of protons. If it has one proton, then it's always going to be hydrogen. If it's got 2 protons, it's always going to be helium. If it's got 3 protons, it's always going to be lithium. So this number here tells us how many number of protons are. This is the number of nucleons. So remember, nucleons are protons and neutrons. So I can look at this and say there's 12 nucleons, there's 12 things in the center, 6 of them protons, and therefore 6 of them are neutrons. Okay, you don't often see this here, but in the symbol notation, you can also write number of neutrons. So if I was to look at something like carbon 14, let's just clear a little bit of wood for me. So that's the most common isotope. I suppose I better just find an isotope. So the number of protons determines the element. But sometimes they'll have different numbers of neutrons. So the number of proton are the number of neutrons determines the isotope. And the number of neutrons in there does make a difference in the isotope. So the isotope is going to have the same number of protons, but it's going to have a different number of neutrons. So if I say carbon 14 is the one used in carbon dating. So carbon 14 says it's got 14 nucleons. Because it's carbon, it's going to have 6 protons. And it's going to have 8 neutrons. Okay, so carbon 14 is very, chemically, there is no difference between isotopes. Well, maybe with deuterium there's a little bit. So isotopes make no or minimal difference to chemistry. Okay, so that's fine. But what isotopes do is they often determine how long will that atom stay in existence. Like this one, carbon 12 is stable. So if you end up with carbon 12 atom, now that lasts for the rest of the universe, basically. This one, what? Every 5,320 years of it, you lose half of it. This will break down into something else, maybe nitrogen, or what would they break down into? Probably beryllium. Okay, but anyway, so the number of the number of neutrons does not affect the chemistry, but it affects the lifespan and how stable that atom actually, or that isotope actually is. So in nature, there's usually 1 or 2 naturally occurring isotopes, because we can also have carbon 13, still carbon, so it's still going to have 6 protons, but it's have 7. We might have carbon 11, still 6 protons, so it's still carbon, but it's going to have 5 neutrons. This will mean these don't tend to last very long because they don't have enough glue in there to hold the whole atom together. So So basically, the number of neutrons says how stable is the atom. Sometimes we want unstable atoms or isotopes for say nuclear power, for radioactivity tracing, for radiation testing, for PET scans. Yeah, we use it for all sorts of things nowadays. So basically, the important thing here, the important takeaway here, is when I have an element, say helium, this number here is protons, this number here is nucleons, so that's P plus N, protons plus neutrons, and this number down here, which is very rarely used but is optional, is neutrons. And with that, we can then go and start talking to other types of radioactivity.